Alright, so in this video I'm going to be explaining an important article with title Multi-Source Domain Adaptation for Text Classification via distanceNet-Bandits. This paper in 2020. Domain adaptation performance of a learning algorithm on a target domain is a function of its source domain error and a divergence measure between the data distribution of these two domains. We present a study of various distance-based measures in the context of NLP tasks that characterize the dissimilarity between domains based on sample estimates. We first conduct analysis experiments to show which of these distance measures can best differentiate samples from same versus different domains, and are correlated with empirical results. And next, we developed a distance net model which uses these distance measures or a mixture of these distance measures as an additional loss function to be minimized jointly with the task loss so as to achieve better unsupervised domain adaptation. This paper from UNC Chapel Hill. Okay, so we described that domain adaptation performance is related to domain distance or dissimilarity. So we will first describe our individual distance measures. We will provide detailed analysis of these distance measures, given source domain samples as well as target domain samples, where we assume X is in RD, are the embedding representation of input data, for example, sentences. The goal of the distance measure is to estimate how different these two domains are. So we have five different measures: L2 distance, cosine distance, maximum mean discrepancy, Fisher linear discriminant, as well as choral. So L2 distance is this one, cosine. We have talked about maximum mean discrepancy in several papers. But you're not familiar with Fisher linear discriminant. Of course, I have explained it in a playlist for machine learning. But Fisher linear discriminant analysis finds a projection where class separation is maximized. In particular, the goal is to give a large separation of class means while simultaneously keeping in-class variance small. This is formulated like this argmax of this. But S sub B in the denominator, you see, this one is the between class covariance. But on the denominator, we have S sub W, and mu C is just, mu sub C is the class mean. Another measure is correlation alignment, choral. Correlation alignment, where the distance between the covariance matrices of source and target samples is measured, and by, of course, the Frobenius measure, because these are matrices, covariance matrices of source and target. So we measure them with this Frobenius norm. And then they have mixtures of distance, this measure as well. This is just a mixture of distance. We have different distances, so it's just a mixture of them. And for distanceNet, the work of Ben David in 2010 shows that domain adaptation performance is related to source domain performance and source target domain distance. The first part is already handled by cross entropy, and it's thus natural to additionally encourage the model to minimize representational distances between the source and the target. To that end, we augment this classification task loss function with the domain distance. So this is the domain distance, and it depends on your choice of distance measure to select what domain distance you want to choose. So we have classification loss, but we also have the distance net. But we will talk about bandit controller. That, this from reinforcement learning, that how it's a very classical problem, and even generalization of bandit, the contextual. And during training a multi-armed bandit controller, so it dynamically dynamically selects the source domains from a set of candidate source domains. The controller updates its belief over the utility of each domain via receiving feedback on validation set. And then we have this, we introduce a novel multi-arm bandit controller charging for dynamically changing the source domain during training. We model the controller as an M-arm bandit whose goal is to select a sequence of action or arms to maximize the expected future payoffs. So at each round, the controller selects an action based on noisy value estimates and observes a reward. More specifically, as the training progresses, the controller picks one of the training domains and have a task model trained on the selected domain using the loss function. So we use the upper confidence bound bandit algorithm, which chooses the action based on the performance upper bound. So this is the upper bound. We call it confidence upper bound. And A sub t is the action at iteration time. So at each time we say which domain should be selected. What is our action? Which domain should be selected? And this QA here is just the action value. For each action we have a value, and is calculated as the running average of rewards. And this n sub t accounts the number of times the action has been selected. The number of times the action has been selected. And then we have this domain separability test that given two sets of source and target domain samples, which are independently and identically distributed. The goal is to find whether these samples come from the same domain or not. For this, we compute the distance between the source and the target samples. So because we have different measures of 1, 2, 3, 4, 5, we have 5 different measures of distance, so we have different results. So the entries on the diagonal refer to the in-domain distances, and off-diagonal refers to the between domain distances. So the first method assess whether distances between samples from the same domain are lower than those between the samples from different domains. This statistic is appealing because it is invariant to scaling and translation, but does not concern how smaller in-domain distances are with respect to off-domain distances. Specifically, we compute the z sub 1 like this. The method 2 says that the second method assesses how smaller the value of the distance between p sub I and p sub I in comparison to distance between p sub I and p sub j. And to compute this, we first standardize the matrix and then apply softmax function to ensure that all the entries are positive. Then we compute the sum of the diagonal entries of the transform matrix as our second quantitative assessment. Lastly, we present the basis for deciding which distances to or not include in the mixture formulation. Now we proceed by removing one metric from the mixture and apply the function phi to give us an estimate of the quality of the reduced mixture. We can now define an estimate of distance measures informativeness. So if this I is small, we can say the removed metric is not informative given other components in the mixture. Here we use the optimal z sub 2 statistic. So we estimate the maximum value using gradient descent. So you see the performance of the baseline compared with the previous work, different models, different data sets. And now, because it's a domain adaptation still, we go from one source to another, to a target domain. And you see the effect of different measures of distance